I confess I like this session because in this session, you folks are going to have to do most of the thinking. So the format it's going to take is we'll talk about different bits, different things that can contribute to performance with MongoDB. We'll give some sample scenarios, and then we'll just do a show of hands in a multi-choice way. So I'll just ask who thinks option A, etc. And we'll see how you perform. So first show of hands, how many people went to the data modeling session that Danielle did earlier? A few, okay. And how many to Asia's indexing session? Okay, so no excuses for getting things wrong. Okay, so I'm Andrew, I'm based in the UK. I've been with MongoDB for 9 years, and before that I had about 6 years as part of the MySQL team at Oracle. So we're going to look at 3 main topics that have an impact on performance. Document sizes, document structure and hierarchy. So for example, whether you nest embedded objects or if you have everything at the same level. And then finally, indexing. So let's start with document size. I think this is probably unnecessary at this point in the day. You all now know what a document is. And so just showing here that in a relational database, if you had customers and phone numbers, you'd have to have 2 tables, one for a customer and then a second one for phone numbers where you have a separate row for every customer. Whereas MongoDB, we just store that as a single document with an array of phone numbers. Okay, so let's start on document size. So this is the scenario we've got. We've got an IoT application, and it's capturing temperature readings from a bunch of sensors. We've got 1,000 sensors, and each one is emitting a reading once every second. The readings are quite simple, contains the sensor ID, the temperature, and a timestamp. And we have to maintain 7 days worth of data. So that means in our database, we've got 605 million readings. I nearly said 605 million documents, but then that would be giving the answer away. Okay, so we're going to look at 3 different schema design options, and then enhance the scenario, and you're going to say which one is best. So the first design, store 1 document for each sensor for each reading. So those documents are pretty small. They've just got the sensor ID, the temperature, and the timestamp or the date. So they're about 70 bytes each. Second scenario is we're going to get a bit more sophisticated, and we're going to store data in buckets. And if you went to Danielle's session, you'll have come across the bucket pattern. So design 2, we have buckets representing a minute's worth of data for a particular sensor. So in our array of readings, we've got 60. And so for our date or our timestamp, we just care down to the minute level. And then for each array element, we store what second within that minute the reading represents. And that's about 2.4K per document. And then the third option is just a refinement of the bucket pattern. But this time, we're saying that for a given sensor, we're going to store an hour's worth of data within the document. So design 1, we get just under 605 million documents. Design 2, 10 million documents. And design 3, 186,000 documents. And as you can see, the total storage varies a little between them because in design number 1, we have to store the full timestamp with every single reading. Whereas when we got the buckets, we're not storing the full timestamp for every bucket. We're just storing the minute and or the second. And we've got a single index on the collection, and it's a compound index on sensor ID and date. So the question is, which collection design will return all of the readings for a specific sensor on a given day faster? So all of the sensor readings for a particular sensor for one 24-hour period. And so we've got the 3 options. Design 1, where it's 1 record per reading. design 2, where it's one record for 60 readings, and answer C, where it's one document storing 3,600 readings for a sensor. So who thinks option A? Option B? Oh, a few people. Option C? Okay, so option C has it. And you're correct. And so the reason for that is that if you look at the number of documents that are having to be returned, in the option 1 it's 86,400 records. And so we're just having to fetch more records from more different places, and so that's slow. Whereas B is somewhere in the middle, and C, we're just fetching 24, so one document for each hour. And so, as you can see, that's fundamentally a lot faster. So, larger documents result in better performance, right? Happy hour time? Rats. As always with engineering, it depends. So, let's look at a different scenario. Which of our 3 candidate schema designs uses the least execution time to add an hour's worth of new data? So, 3.6 million new readings. So for option 1, we're going to do an insert many, so we're going to do a bulk insert. And so every second, we're receiving the readings from all of the sensors. And so we insert many, and so for each sensor, for that second, we store the document. In option B, we're using the bucket pattern. And so we push the new readings onto the array for that sensor. And then if we don't already have a document for that sensor for that minute, because we've set upsert true, we'll create a brand new bucket document for that sensor for that minute. And then for the third option, it's very similar, except we're now having to record all of the data for a particular hour. So we're inserting the temperature, the minute, and the second within the hour. So, which one consumes the least time? So who thinks it's option A? Oh, a few people are jumping in. Okay. Option B? Option C. Okay. Option A. A hint. It's never option B. Okay. And so the reason for this is, if you just look at the numbers, well, it's basically because inserting lots of small documents is actually pretty quick. As documents get bigger, it gets more expensive to make changes to that document. Because as soon as the document goes above 32 kilobytes, you're writing as the document gets bigger and bigger, you're having to write the entire document back to disk behind the scenes. And you're having to compress the data. So if you've got a 100 kilobyte document and you make the smallest change to it, you've got to compress 100 kilobytes and then write 100 kilobytes back to disk. Or at least that's what MongoDB is having to do behind the scenes. Okay, so now we're saying smaller documents are better. Oops. So to understand how this works, let's look a bit at how caching works in MongoDB. So when we store data on disk, we try and store 32 kilobyte blocks of data on disk. So that's before compression. So if you had a 32 kilobyte document, we would store that as a single block on disk. And so if we imagine this, where we've got documents that are 8 kilobytes each, in one of these blocks, we can fit 4 documents. before we hit that limit. And then when we add another document, this one happens to be 12 kilobytes, that goes into a second block on disk. And we add another 8 kilobyte document. We're now storing 20, then 28 kilobytes in that single block. And now we go ahead and add Pavel, and that actually spills over. It doesn't fit within the previous block, so we have another disk block, and that's where Pavel is going to be stored. And then again, Rita fits in there as well. Chuck fits in there. Matt actually has a much bigger document, and so he gets a block all to himself. So if he's 50 kilobytes, he gets a 50 kilobyte block. And so why is this important? Well, one of the aspects is that when you read a document from disk into cache, you don't just read that single document. You read the entire block. Similarly, if you make a change to a document, so that gets updated by the application, updates the document in cache in MongoDB, and then it's not just that single document that gets flushed to disk or copied to disk, it's the entire block of documents. And so in this case, we've got 4 documents in the first block, so we change any one of those documents, the entire block gets written back to disk. Okay, so let's work from a scenario where we've actually got quite a small cache. And we've got these 5 documents in cache at the moment, and that's filling up our entire cache. No, it isn't. Okay. And so now we do a query saying we want to read or find the document for Daniel. So that reads in Daniel plus all the other documents in the same block. And so the consequence of that is that there's no longer space for Matt in cache, and so we've purged Matt from the cache. And if Matt was a document that we updated frequently, that's not great, because the next time we want to access Matt, we have to go and fetch him from disk again. So it's important to bear in mind, as I say, in that scenario where we've only got lots of tiny documents, every time we read one of those documents, it's bringing in a whole load of other documents that we don't care about. And so it's pushing some of the data we do care about out of the cache. And so have you seen for this same data set, we get radically different schemas based on whether we want to optimize for inserting the data, reading the data for a given sensor for an hour, etc. If our primary query was find me the average across all sensors for a particular point in time, then we may come up with a different schema again. So you really need to understand how you're going to use the data before you come up with the optimal schema. Okay, so the structure within your document. So as you should have learned by today, one of the big differences with Mongo is you don't have to have individual columns which are scalar values. You can have embedded documents. You can have arrays. We can take advantage of those. As we've already seen in a relational database, this is how you're meant to model a customer with their phone numbers, with a one-to-many relationship. How people actually end up implementing that, because people realize even with a relational database, doing a join just to get a customer and their phone numbers is a bit over the top. So you'll see people storing a string with a comma-separated list of phone numbers. You'll see people trying to be sophisticated and store an XML document. Or people will actually go and add multiple columns. And so for the maximum possible number of phone numbers, they'll have a column for each one. And in most cases, most of those are set to null. Whereas, as we've seen, with MongoDB, we store it as a document. And this is an example of a document where we have added some hierarchy and some structure. So we always have the underscore ID, so that's always going to be at the top level. We have a document representing the name, and within there we have first, middle, and last. We have a field representing the phone numbers, which is just an array of objects. Okay, so document hierarchy. So we've got 2 candidate document designs for our collection. containing this customer information. The collection is going to contain 10 million customer documents. So in both cases, we're going to have one document per customer. And each document contains 300 data fields, so a bit more than I showed there. And the value of each field is a scalar, so we've got no embedding, no arrays, no embedded objects. And the only index we're going to have is on the underscore ID. So the default indexes. So our first design, we're going to go a very simplistic approach and have all of our fields as top-level scalar values. So we've got 300 fields all at the same level. And the field we actually want to search on is account tier, which just happens to be near the bottom of the document. In the second option, we're going to add some structure. So the only scalar at the top level is underscore ID. Then we've got embedded objects for the customer details, etc. And the information or the field we actually want to filter on is within the rewards metadata object, and it's the account tier. OK, so running this query, which document design is going to return faster? So we're doing a search in this case where the ID is between 30,000 and 40,000, and the account here is platinum. For the second design, the query is slightly different because we have to query on rewards metadata dot account tier. And again, remember, the only index we've got is on the underscore ID. So which one's going to be faster? Who thinks A, where we've got a flat structure? A few people. Who thinks B? OK, a majority of people. This is a fun one because a very common question I get in design reviews is how many levels of nesting is too many? And in reality, the question should be how many levels of nesting is too little? Because most of you got it right, that adding the structure speeds it up. How much do you think it sped it up by? 10% faster? 25? 50%? OK, you guys just think it's going to be the biggest number every time, don't you? They're OK. And the answer is yes, 50% faster. So what's the reason for that? Let's look at what's involved when you run a query. The first stage is we go and find an appropriate index if one exists. And then once we've found that index, we're going to navigate that index and get effectively the pointers to the documents that we care about. We're going to fetch them. So if they're on disk, we'll fetch them into the cache. And then we can apply additional filters. So this is any part of the query that wasn't included in the index. And then we're going to do the projection. So get rid of any fields we don't care about, maybe add some computed fields in there. So the hierarchy affects this filter point. So it's where you've potentially narrowed down the set of documents using an index, but you still need to examine one or more additional keys. And so why does that take longer? It's down to the fact that we're a document database, and we don't fix that for a given collection, the first column always contains the first name. The second column always contains the second name. You could have different documents in the same collection which have a different key as the first part of the document. And so on the right-hand side, this is how we actually store a document in MongoDB. So for each field, we've got a row here. Some of the fields have got a fixed size, like an int 32. It's got a fixed size. But others, such as the string or a document, it can be variable size. So for those, we store how big or how many bytes that represents. So that means that when we're trying to filter on a non-indexed field, we can navigate the object. So we start at the beginning and say, is the first field, is the key I'm trying to filter on called _ID? No, it isn't. So I know I can jump ahead to the next field. Is the key name color? No, it isn't, etc. And so it navigates through that structure. And so if we take the example of the flat structure, then when we want to get all the way to the bottom, so in this case, we want to filter on the version, and that's the last field in the document. In this case, we've actually got to iterate, and we've got to look at every single key until we find a key that is called version. And then, only then, can we actually say, yes, this is the field we care about, and we can filter on the version number. Conversely, if we add a bit of structure to this, then we can, let's go back. We can take shortcuts. So we navigate through, but when we hit the key named application, in the document we know it's a certain size, so we can just jump ahead and skip over all of those fields within that embedded object. So now instead of having to iterate through 10 fields, we've only had to iterate through 5. So this is a simple example, but imagine cases where you've got 300 fields, 1,000 fields. I've heard today 3,000 fields. Sort of that actually becomes expensive to do that. And it's not just when you're doing the filtering, it's also when you do the projection. So even if you did a query on the _ID, and so it uses the index, and you said you wanted to project out everything apart from the version, you'd still have to go navigating this just to find the fields that you care about. Okay, the next question is going to be pretty easy. So in our last scenario, we saw that document hierarchy can improve scan time. How else could we improve execution time? Anyone want to have a hint? There's been no hints here. I didn't write these slides, by the way. Okay, so indexing. So how can we improve this situation? So again, remember only the _ID was indexed. So we're doing a query where we want to find, so it's the same query actually, that the ID is, _ID is between 30,000 and 40,000, and the account tier is platinum. So let's start off by looking at the explain plan. So how many people here use MongoDB Compass? Okay. So anyone who's using MongoDB and you're not using MongoDB Compass, use it. So it's a desktop tool. It's completely free to download. And you can run queries within there, but the bit I like is I can just go ahead and click on that button that says in tiny font, explain, and it's going to give me the execution plan, or the explain plan. You can do this from the Mongo shell, but it's going to give you a whole load of JSON, and you've got to go and parse through that. So I just find it much easier to use the visual plan in Compass. So if that query we ran, let's look at what it actually told us. So it used the index on _ID, so that's good, because we were querying on a range of _IDs. So we looked at, is that 100,000 keys in the index? We found 10,000 documents that we wanted to look at. So that means that there were 10,000 documents where the _ID was in that range. And then it has to scan through every one of those 10,000 documents until it finally gets to the 2006 documents that actually meet the criteria. So this is a great example where the index has done part of the work for us. We've not had to do a full collection scan, but we've still looked at more documents that we needed to. We've still brought more documents into cache and had expensive disk reads than we really needed to. So what could we do to fix that? So we've seen that hierarchy improves it. How else can we improve it? Get rid of unnecessary document scanning by adding account tier to our index definition. So this is simple stuff for anyone who went to Asia's session. And so we add our index, so db.customers.createIndex, account here, and then underscore ID. Oh yeah, so that's in our first option, but where we have the hierarchy, the index is slightly different because we've got to add it on rewards, metadata, .account here, and then underscore ID. Okay, so by including both queried fields in our index definition, how much faster will our queries execute? So almost twice as fast, almost 3 times as fast, more than 10 times as fast. So A, B, C, rats, you've figured out the scheme. So yeah, so where we've got the flat structure, it goes down to 39 milliseconds from nearly 500. And interestingly, now having the hierarchical structure barely changes the time it takes. And the reason for that is that because we're now no longer having to do that filter stage. So the index is doing all of the work to get to the exact documents we need. And if we go back to the explain plan, we can see that we're now using our new compound index. Again, we're examining just over 2,000 keys, which is the same as before. But now we're only looking at 2,000 documents, and we're returning all 2,000 of those documents. So now we're seeing that the index is doing all of the work, and we're not having to fetch documents into cache just to look at them and then discard them because they're not part of the results. Okay, so again, anyone who went to Asia's session will be aware of this. The order of fields in an index can make a difference. So here we had the account tier first, and then we did the underscore ID second. So what would happen if we reversed that? So we had the underscore ID first and then account tier in the index. So who thinks the A, it would execute faster? B, it would be slower. Okay. C, it would be more or less the same. Okay, so it's about 50-50 between we'd slow it down and it would be more or less the same. The answer is it would execute slower. And so it goes down from so it goes, instead of 39 milliseconds, it goes up to 177 milliseconds. And if we look at the explain plan, we get some hints as to why that was the case. So it's used our new index where we've got ID first. And it looked at 2006 documents. So it only looked at the same number of documents. So no clue there. But if you remember, first time round, it looked at far fewer documents. So within the index, it's having to look at more elements within the index. So it's not having to fetch more documents from disk or anything like that. But the index work is greater because of the order that we're looking for the keys in there. So I didn't go to Asia's session, but I assume she introduced you to an acronym. Is there an acronym to explain this? ESR, that's good. So when you're coming up with the order that you put keys in a compound index, the order you try and do it is equality, sort, and range. So in this case, the equality part of our query was that the account tier equals platinum. And then on the underscore ID, we were performing a range. So this means that we followed the ESR rule, and it was significantly faster. And if you want more information on the ESR and why this is the case, then that QR code will help you. OK, so having queries fully supported by index is crucial, but can we make things even better? Any suggestions? No? OK. Covered queries. So we've got the same query, but we're now adding a projection to say that the only results we want returning is the underscore ID and the account here. So that means that all of the information that we need to reply to the application, it's all actually within the index. So that means we don't actually have to go fetching documents. So how much faster do you think it got because we had a covered query rather than actually having to look at fetch the documents and look at the documents? Who thinks 2 times faster? Who thinks 10 times faster? Who thinks 15 times faster? It's getting tense. And you're all wrong. 2 times faster. But there's something we haven't discussed in the setup for this. Does anyone know what information I could have given you that may have let you have a better guess? Sorry? Yeah. So the first time I saw these slides, I had to contact the guy who wrote them. And the question I had for him was, when you ran these tests, were all of the documents already in cache? And the answer was yes. So in this case, we did have to look at the documents, but they were already in cache, so it didn't cost us that much. So if you had a more realistic scenario where not everything was in cache, then yeah, you may see 10 times faster, 15 times faster. So it's a little bit of a trick question. Right, let's look at our explain plan again. So now we can see that we used our index. It's been flagged that we had projection covered. And it's confirming that we returned the same 2,000 odd documents, but now we didn't have to look at any documents. So we just used the information that was in the index. So takeaway, use sensible document sizes for your workload. And as we've seen, it depends on what you're trying to optimize for. But we've got a general rule that if the document's no bigger than 200 kilobytes, don't worry about it being too big. As you've probably guessed, the absolute sweet spot is usually 32 kilobytes, because that matches the block size. But also try and avoid having queries where you're fetching hundreds or thousands of tiny documents, because then you're having to fetch all of that data from different places, potentially from different spots on disk, and so that gets expensive. In your document hierarchy, don't be afraid of having hierarchy. If you have to go to 5 levels deep, that's fine. And when people ask me what the right depth is, my usual response is, yeah, try and avoid having more than 200 fields at the same level. But the real thing is, what would you do if you were defining a class for that document? So if this was a programming language and you wanted to have a sensible class, you'd probably do things like, I'm going to embed the employee name within a subclass. I'm probably going to embed all of the fields of the address. And so just do the same thing as you would for classes with your document definitions. And indexes, absolutely, they're very important that you have indexes for your frequent queries. As you've seen, they're going to make the queries much, much faster. But also remember that there is an overhead. There is a cost to each index you have. Because every time you have an index, if you insert a document that's got 5 indexes in, you've got to go and update 5 indexes. And there's a cost to that. And very roughly, each additional index you add slows down the writes by about 25%. So if you add 4 additional indexes, you've probably slowed down your inserts by 100%. And if you make a change, every key that you change, which is in an index, you've got to go and update that index. So just bear that in mind. And one of the most common mistakes we see is people will have a compound index that is on fields A and B. And then they also have an index which is just on index A. So the index that's just on key A, that's wasted, because the index that's on A and B, that'll be used for queries that are just on A. It won't be used for queries just on B, but it'll be used on queries that are just on A. And if you use Ops Manager, if you're using Enterprise Advanced or the Performance Advisor within the Atlas UI, it will actually make recommendations. So it'll tell you that I've been seeing a lot of queries that don't have an index. I suggest this index. It'll also say, I see an obsolete index. You can get rid of this one. So make sure you just go in there and check what's going on in your system. And a final thing is, if you want to try some of this stuff out for yourself, so for example, if you want to repeat some of the tests where the documents aren't already in cache, then this is the repo that everything is in. And then it's got the specs of the particular cluster we were running on as well. So that's all I had. We have got a few minutes left. So does anyone have any questions?
Does any of this apply to the online archive?
Does it apply to what, sorry?
To the Atlas Online Archive.
The Atlas Online Archive. No, the Atlas Online Archive is a different beast. So with the online archive, the data that's archived, it's stored in S3. Then your performance when you're querying it is going to come down to what you chose for the partitioning of the data. And so rather than defining indexes, you define partitions, which means that, for example, in our sensor example, we could have used the sensor ID as the partition key for S3. And so that way, when we're trying to get all of the data for a particular sensor, they're going to be in the same set of files. Whereas if we went for that scheme and instead we said, find me all of the readings for all sensors at this particular time, it would have to go and look at lots of different files in S3. So we don't have indexing with Online Archive, but you have similar kind of optimizations you can do with partitioning.
Anybody else?
Okay. I like this. We're going for... Oh, I thought you were going to go right to that corner. And then I've paid him to ask the next question.
Are there any efficient ways of assessing the dot size, say in like Compass, of documents in like large collections? And
is there an easy way of looking at the document size for something like Compass? Absolutely. So on Compass, that people have used it, on the left-hand side, you have the list of databases, and then within each database, the collection name. If you click on the database name rather than the collection name, then it'll give you a summary for each collection. And in there, it'll include the average document size. Like I say, if you're using MongoDB and you're not using Compass, you use Compass. It's completely free, and it's really cool.
Probably I missed, but I just want to ask to you, when we make projection while finding documents, is it saving to cache as a projected version or full document?
Yeah, that's a good question. So when you do a query that involves a projection, projections are done after the document is brought into the cache. Okay. So we don't do anything, because bear in mind, it's not just bringing that document into cache, it's bringing the whole block.
Okay.
So it's all brought into cache, and then you do the projection and so if every time you're querying you do a projection and you're throwing 90% of the data away, then that's a hint that maybe you should look at breaking the document up. Yeah. So you're not bringing all of that other 90% that you're always ignoring.
Okay, what if in the cache, for example, all document fields in the cache, and we make same query again, from the getting cache, is it difference between?
Yeah, so once the document is in cache, okay, and it's always the entire document that's in cache, then you can query it with lots of different projections, and it's still going to use that cached version of it.
Okay.
Sort of, we don't have anything like you might have a query cache in something like MySQL, where you actually cache the results of a particular query. Sort of, we're only caching the whole documents.
Thank you so much.
So you mentioned in the, like when we talk about the filtering, you mentioned explicitly that we're looking for a field that's like at the end of the table, like at the end of the document.
Yeah.
So for a realistic document, you have like 50 fields, say. How much does it matter when you query, like in that filter stage, where you look for a field that's the first field versus the last field? Like how much slower is that operation depending on the order of?
So what can we go back to? Boom, boom, boom. The animation seemed such a good idea at the time. Okay. Getting closer. Because the answer is I don't remember the numbers, so we have to go back. So in this particular case, we added the hierarchy. So we went from, so I think it was we had, was it 300 fields we had? I think it was 300. Yeah, so we had 300 fields. So in the case where we had all the 300 fields at the same level versus when we had the hierarchy in there, we were seeing that it was 50% faster. So you could kind of probably work it out linearly.
Sure, but you went from 300 to like 5. Okay, fine.
Yeah. So it can be quite significant. If the documents weren't in cache, then the impact would be a lot less because the cost of fetching them from disk into cache is higher than iterating through it. But so this would, like I say, if we didn't have everything in cache, the effect would be less because everything would be dwarfed by the latency of going to disk.
Sure, but then also if you were to query in the flat structure by like the second field, then the difference would be negligible.
Yeah, exactly.
Okay.
So it's chance.
Okay.
Yeah.
Anybody else? Yeah.
In the indexing talk earlier, we were told that people use descending indexes wrong a lot.
Use what, sorry?
Descending indexes, as in a field -1.
Okay, descending indexes, yeah.
Yeah. But we weren't told when we should use those. So I wonder if you could comment on that.
I don't know. I haven't seen this version of Asia's talk, so I'm not sure. But yeah, when you're defining indexes, you can say whether it's ascending or descending, where the idea is that when you do a sort, if you're saying sort ascending, then an ascending index is better. If you're doing descending sort, then descending is better. But I'm not sure what the particular sort of bad practice was.
I heard someone ask that question later in person.
Yeah.
And the answer was, if it's a one field index, then it doesn't matter because it will do ascending or descending regardless. But if you have a multi-field index and you need one of the fields to be ordered in one way and the other in a reverse way, then you can choose to put them the other way around.
Okay, cool. Thank you.
Anybody else?
No.
I think it's a prop.
Okay, so thanks everyone. So I think happy hours in the expo hall
Yeah.
starting now.
Thank you, Andrew.
Oh.
Thank you.